Hello friends and welcome to CEC online lectures. In the previous few lectures I have discussed about certain important classes of plant secondary metabolites like alkaloids, flavonoids and volatile oils, and in those lectures we discussed that how these are defined, what is their distribution in nature, how they are biosynthesized in the plant matrix and how they are extracted from the plant matrix. We also discussed their properties, their classification. We discuss various classes with suitable examples, and in the end we discuss about their important therapeutical uses. So friends, today I am going to start with yet another important class of secondary metabolites, that is terpenoids. Now in this lecture we are going to learn that what are terpenoids. Then there are certain general chemistry rules that govern the structure of these terpenoids. So we are going to discuss what are those chemistry rules. Then we will discuss about the properties of terpenoids, then their biosynthesis, how these are synthesized in the plants, then how these are classified, because terpenoids are such a diverse group of the plant secondary metabolites, so they have varied structures. So how these structures are classified, or what are the basis of the classification of these diverse structures, we are going to discuss in the classification part of the terpenoids. And in the end we will be discussing about important therapeutical uses of terpenoids. So friends, it all began in 1818 when Houston started analyzing turpentine oil, and he found that it possessed certain important hydrocarbon compounds. Though he was not able to give a specific name to these hydrocarbon compounds, but he was the person who first analyzed that the turpentine oil contains certain hydrocarbon compounds. Later in 1866, Dumas gave the term terpenes to these hydrocarbon compounds. And since these compounds were isolated from turpentine oil or identified from turpentine oil, the name terpenes was given to such compounds. Now the term terpenoid has been generated from this generic term terpene, but there is a school of thought which still believes that the term terpene should be restricted to the compound or the hydrocarbon compounds that were isolated from the turpentine oil. But nowadays, by and large, you will see that the term terpene or terpenoid is being used interchangeably. Now, what is the difference between terpenoid and a terpene? Basically, terpenoid are the compounds that are oxygenated derivatives of terpene, and therefore I said that these terpenoids, the term terpenoid has been generated from the generic term terpene. Since they are oxygenated derivative or functionalated derivatives of terpenes, the term terpenoid was given. And as I told you that now by and large terpene and terpenoid terms are interchangeably used, and for our convenience I'll be using the term terpenoid throughout my lecture. Now we move on to the general chemistry rules that govern the structure of these important secondary metabolites, and the first one is the Isoprene rule, which was given by Otto Wallich in 1887. And according to this rule, these terpenes or terpenoids are the compounds which are made up of isoprene units, which is having a formula of C5H8, as you can see the structure of an isoprene unit on your slide. Now, he also stated that since terpenes are made up of isoprene units, these are now sometimes also called as isoprenoids. So in short, the Isoprene rule states that terpenes or terpenoids are the compounds which are made up of isoprene units. After Wallich in gold in 1925, he gave another rule which is known as special isoprene rule. When he was studying about the structure of terpenoids, he found that these isoprene units, they have a specific orientation in the structure. So therefore he gave this rule, and according to this rule, the isoprene units in the terpenoids, they are present in a head to tail orientation. So as you can see in the slide, structure of isoprene unit has two parts. The bifurcated portion is known as the head part and the other portion is known as the tail part. So according to Ingold, the isoprene units present in the terpenoids have a head to tail orientation, means the tail of one isoprene unit is attached to the head of the another isoprene unit. So this was the special isoprene unit. But there are certain exceptions to this special isoprene unit. So as you can see, lavandulol is one exception wherein the isoprene unit are attached through tail-to-tail configuration, and likewise in carotenoids also, which are considered as another polymer type of I will say terpenoids or isoprene units. Here again the isoprene units are attached in a tail-to-tail configuration. So these are the two examples of exceptions of the special isoprene rule. Now another rule that governs the structure of these terpenoids is the Gem-dialkyl rule, which was again given by Ingold in 1921. And this rule is more applicable to mono or bicyclic monoterpenes as well as sesquiterpenes. Now according to Gem-dialkyl rule, it states that if a Gem-dialkyl is present on a cyclohexane ring in case of monocyclic monoterpenoids, it makes the structure of monoterpenoids highly unstable. And since the monocyclic monoterpenoid have only one cyclohexane ring, the variability in the structures in their structure is highly limited. And therefore, as we will see during the classification, when we will discuss the classification of monoterpenoids, we will see that majority of the monoterpenoids are the derivatives of paramethane when a cyclohexane ring is present, or paracymene when an aromatic ring is or unsaturation is present in their structure. So by and large, we can say that as per Gem-dialkyl rule, the dialkyl group should not present on the cyclohexane ring, rather than it should be present on outside or on the side chain of the ring. Now coming on to the bicyclic structure, and since they have two rings in their structure, so this allows structural variability in case of bicyclic monoterpenes or sesquiterpenoids. Since Gem-dialkyl cannot be present on the cyclohexane ring, it should be present. It should be present on the other ring in case of bicyclic monoterpenes or the sesquiterpenes. So here I'll be considering monoterpenes first. Now since as I told you, because they are having two rings in their structure, so this allows them to have different structures, or this allows to have them structural variability. So as you can see on the slide, these bicyclic monoterpenes can have 6+5 system, where one ring is cyclohexane and the other ring is cyclopentane, and such structures are found in camphor, or compounds having such kind of structure are known as campaigns. They can also have a 6+4 configuration system, where one ring is cyclohexane and other ring is cyclobutane, and if such ring structure is present, such compounds are known as pinanes. And they can also have a cyclohexane ring along with a cyclopropane ring, which forms a 6+3 system, and such kind of compounds having 6+3 system, they are known as carenes. Now according to Gem-dialkyl rule, the dialkyl group cannot be present on the cyclohexane ring because it will make the structure unstable, but this Gem-dialkyl or the dialkyl group can be present on the second ring, which is the smaller ring. So it can be either present on the cyclopentane ring in 6+5 system, it can be present on the cyclobutane ring in the case of 6+4 configuration, as you can see in the structure of pinanes, or it can be present on the cyclopropane ring in case of carenes. So this was in total the Gem-dialkyl rule, wherein it states that the dialkyl group should not be present on the cyclohexane ring, which will make the structure unstable. Now we move on to the properties of terpenoids. Majority of the terpenoids are optically active, and in the nature you will find their isomers some of the isomers even have different pharmacological activities or the therapeutical activity. Either some of the isomers are more active than their counterparts. As we discussed that monoterpenoids or sesquiterpenoids are the major components of the volatile oils, and since they are the major component, they are responsible for the fragrance of those oils. So we can say that majority of the terpenoids are they have their specific fragrance, and most of them are liquid in nature, with an exception of camphor, which is commonly known as kapoor, and we all know that it is solid in nature and it get volatilized whenever it is exposed to air. Majority of the terpenoids are lighter than water, and we have observed the same property in case of volatile oils also, which are lighter than majority of the volatile oils are lighter than water. Since they are mainly composed of mono and sesquiterpenes, we can say that these are lighter than water. Most of the terpenoids are insoluble in water, and they are largely soluble in the organic solvents like chloroform, ether or diethyl ether or dichloromethane or alcohol or methanol, so on and so forth. They can also undergo polymerization or dehydrogenation reactions, and whenever these terpenoids are exposed to thermal decomposition, they give rise to isoprene units. As we have discussed that terpenoids are made up of isoprene units, and whenever they are thermally decomposed, specifically in case of polyterpenoids, wherein if we subject or expose rubber, which is a polyterpenoid, to thermal decomposition, it will give rise to isoprene units. So this was in brief about the properties of terpenoids. Now we move on to the biosynthesis of terpenoids, and as I told you that these terpenoids have a diverse structure or diverse variability or in their chemical structure, but they are largely synthesized through a pathway which is known as mevalonic acid pathway. As I discussed in my previous lecture of volatile oils, that the constituent or the volatile oil or the constituents of the volatile oil are synthesized through mevalonic acid pathway. Since they are mainly composed of terpenes, so here we can also say that terpenoids, they are biosynthesized largely through the mevalonic acid pathway. But apart from mevalonic acid pathway, these terpenoids can also be synthesized through non-mevalonic pathway or non-mevalonate pathway. Now, this type of pathway is also known as 2,C-methyl d-erythritol 4-phosphate, that is MEP pathway, or it is also known as 1-deoxy d-xylulose 5-phosphate, that is DXP pathways. Now, mevalonic acid pathway has been found to mainly occur in mammals, cystole or the mitochondria of the plants, or in certain fungi. Whereas the non-mevalonate pathway is more prevalent in case of eubacteria, blue-green algae, cyanobacteria, and in case of higher plants. Now we'll discuss about this mevalonate pathway. Now, as you can see in the slide, and as I told you that terpenoids show enormous chemical and structural diversity, but the biosynthesis, it occurs, or the backbone of the biosynthesis, it starts with only acetyl-CoA, and their backbone is made up of two precursors, that is isopentyl pyrophosphate, that is IPP, and its isomer, that is dimethyl allyl pyrophosphate, DMAPP. So as you can see in the biosynthetic pathway, that it starts with the two molecules of acetyl-CoA, which get condensed with the help of acetyl-CoA synthase, and it gives rise to acetoacetyl-CoA. Now, to this molecule of acetoacetyl-CoA, another molecule of acetyl-CoA gets condensed with the help of HMG-CoA synthase enzyme, and it gives rise to 3-hydroxy-3-methyl-butyryl-CoA, which is 3-HMG. Now, this 3-HMG undergoes reduction reaction with the help of two NADPH molecules and HMG-CoA reductase to give rise to mevalonate. Now mevalonate undergo couple of reactions with the help of mevalonate kinase and phosphomevalonate kinase utilizing two ATP molecules. Undergo phosphorylation to give rise to mevalonate 5-diphosphate, which further undergoes decarboxylation reaction with the help of mevalonate pyrophosphate decarboxylase to give rise to the first precursor of the terpenoids, which is known as isopentenyl pyrophosphate or IPP, which can get converted into its isomer, which is known as dimethyl allyl pyrophosphate, that is DMAPP. Now, for mono or the high terpenoids, as we discussed that the starting molecule is either IPP or DMAPP. Now, DMAPP further undergo condensation reaction with IPP unit, another IPP unit, to give rise to geranyl pyrophosphate. Now, this geranyl pyrophosphate, it leads to the formation of geranyl diphosphate, which is a precursor of monoterpenes. And when another IPP molecule gets condensed with this geranyl diphosphate molecule, it gives rise to farnesyl diphosphate or farnesyl pyrophosphate molecule, which is FDPP or FPP. Now, this FPP again acts as a precursor for the synthesis of sesquiterpenes, and if another IPP molecule gets condensed with this FDPP, it gives rise to geranyl diphosphate or geranyl pyrophosphate. Now, this GPP again acts as a precursor for the synthesis of diterpenes, and if another IPP molecule gets condensed with GPP, it gives rise to farnesyl geranyl diphosphate, which acts as a precursor of sesterpenes, and likewise various other isoprene units get condensed with these precursors to give rise to triterpenoids or tetraterpenoids or polyterpenoids. So if we want to summarize the biosynthesis, we can say that the active isoprene units or these IPP units, which are also known as isoprene units, if they are repeatedly added to DMAPP or prenyl diphosphate in a sequential head to tail manner or condensation, which is such reactions are catalyzed by prenyl transferases, they give rise to different classes of monoterpenoids. So, for mono or higher terpenoids, we can say that the IPP unit get condensed with DMAPP to give rise to geranyl diphosphate or pyrophosphate, as we can see in the slide, which leads to the synthesis of monoterpenoids. Now, after monoterpenoids, sequential condensation of IPP with GPP leads to the formation of FPP, which further give rise to sesquiterpenes, and so on and so forth. We get sesterpenes or diterpenes, and finally condensation of appropriate intermediate or the precursors or the IPP units. It leads to the synthesis of tri, tetra or the polyterpenoids. So friends, this was all about the biosynthesis of terpenoids. Now we move on to the classification of terpenoids. So as I told you that they have a diverse chemical and structural variability, or they have terpenoids have large variation in their chemistry or in their structure. They are classified into different classes. And further, since these are made up of isoprene units, the classification of terpenoids is largely based upon the number of isoprene units that are present in their structure. Now, these classes, subclasses of terpenoids can further be classified on the basis of the structure, whether it is an open chain. If it is an open chain, it is an acyclic terpenoid, and if it is having a cyclic structure, they are known as cyclic terpenoids. Now, cyclic terpenoids, depending upon the number of the rings present in their structure, can be further classified into monocyclic, bicyclic, tricyclic, tetracyclic, and so on and so forth. So coming on to the classification, you can see in the table that if the terpenoids are having one isoprene unit, they are known as hemiterpenes. But as per the definition of terpenes or terpenoids, they must possess two or more isoprene units. Obviously, if isoprene unit is having C5H8 configuration, then hemiterpenoids will be having only 5 carbon atoms. Then if there are two isoprene units present in the structure, they are known as monoterpenoids and they will be having 10 carbon atoms. Then sesquiterpenoids are the class which are having 3 isoprene units and 15 carbon atoms. Likewise, diterpenoids are the compounds having 4 isoprene units and 20 carbon atoms. 5 isoprene units are present in sesterpenes and therefore they have 25 carbon atoms. 6 isoprene units are present in triterpenoids and therefore they have 30 carbon atoms. And if there are 8 isoprene units present in the structure, such type of terpenoids are known as tetraterpenoids and they have 40 carbon atoms in their structure. Now, if there are more than 8 isoprene units present in a structure, such an terpenoid is classified as a polyterpenoid. So, in short, we can say if a terpenoidal structure is having more than 8 or 10 isoprene units, it is categorized as a polyterpenoid, and the most common example of a polyterpenoidal structure is rubber, which is having more than 100 isoprene units and therefore the carbon atom is more than 100. So now we are going to discuss each and every class with suitable examples. Coming first to the monoterpenoids. So as we have seen that it contains 2 isoprene units and therefore it is having 10 carbon atoms. And as we have already discussed in the previous lecture that majority of the volatile oils have monoterpenes as their major components. Now, as I told you that these monoterpenoids can further be classified on the basis of the structure, whether it is acyclic or cyclic. Likewise, monoterpenoids are also classified as acyclic monoterpenoids and cyclic monoterpenoids. And if a single ring is present, then they are known as monocyclic monoterpenoids. And as we discussed in Gemalkyl Rule, that majority of the monocyclic monoterpenoids are paramethane derivatives or they have a paramethane skeleton. So if 2 rings are present in monoterpenoidal structure, they are known as bicyclic monoterpenoids, and they can and since bicyclic have large structural diversity, they can further categorized into thujane type, pinene type, fenchane, camphane type skeletons. Now, apart from since these cyclic or acyclic monoterpenoids, they follow the specific special isoprene unit rule, which states that the isoprene unit are attached in a head to tail configuration. So acyclic and cyclic monoterpenes, they have a head to tail attachment of isoprene unit. But there are certain monoterpenoids which do not have a head to tail attachment, or we can say they either have head to head or a tail to tail attachment. Such monoterpenoids are known as irregular monoterpenoids and they have been separated, they have been classified as a monoterpenoid iridoids. Now, discussing monoterpenoid iridoid will be beyond the scope of this lecture, but briefly I'll tell you that these iridoids are important bitter compounds like amarogentin is there, gentiopicrin is there. These are the seco-iridoid compounds which occur in the glycosidic form and they are highly bitter in nature. So now coming on to the acyclic monoterpenoids. So as you can see, there are different examples of acyclic monoterpenes like myrcene, ocimene, and since they are optically active, you can see different isomers. Then we have the oxygenative derivatives of the terpenes also like linalool, geraniol. Now, linalool is a compound which is largely found in the volatile oil of lavender, which is Lavandula angustifolia. You can also find linalool in case of Coriandrum sativum, which is commonly known as dhania. Then another example is geraniol, which is largely found in the essential oil of Cymbopogon species and is largely used in perfumery. Likewise, we have other examples of acyclic monoterpenoids like geraniol, which is an aldehydic or oxygenative derivative. Then its isomer, that is needle, isocitral, and citronellal. Citronellal is again an important compound which is found in Cymbopogon species and also found in Melissia officinalis and in various eucalyptus species, and has a important role in perfumery industry. So this was all about the acyclic monoterpenoids. Now we move on to the cyclic monoterpenoids, or the monocyclic monoterpenoids, where only one ring is present. And as I told you, that majority of these are having paramenthane structure. So the various examples are menthol, which is the most common example of paramenthane or the monocyclic monoterpenoidal structures. And we know that menthol is largely found in Mentha piperata, which is having wide usage in perfumery, in cosmeceuticals, in other pharmaceutical as a taste masking or as a flavoring agent in confectionery also. Then we have limonene, which is found in citrus fruits, again used in perfumery because of their fragrance. Caravol in case of caraway, because that specific odor is largely due to caviol. Then we have 1,8-cineol, which is also known as eucalyptol, and it is largely found in the eucalyptus species. Now we move on to the bicyclic monoterpenes, and in this we further have classified on the basis of the structure as thujane type, which are having a cyclopropane and a cyclohexane ring. So these are the example, and cyclopropane ring is within the cyclohexane ring. So we have examples of thujane, which is a saturated form, and thujene, which is an unsaturated form. Likewise, thujol is there, which is an oxygenated derivative. Alpha thujone, which is ketonic, or we can also say that it's also an oxidative derivative of thujane. Then again the isomers of thujone, and so on and so forth. Now these thujane and their oxidative derivatives have been found in different species belonging to genus Thymus or Juniperus or Artemisia. Now the next subclass of bicyclic monoterpenoid is of pinene type, and as we have discussed that they largely possess a cyclobutane and a cyclohexane ring, and you can see that the dialkyl group is present on the cyclobutane ring, which makes the structure highly stable. And the common examples are pinene, both alpha and beta pinene, which are largely found in the pine trees. Then we have a third subtype of bicyclic monoterpenoids, which are phenchane type, and they have two cyclopentane rings, and one cyclopentane ring is present within the another cyclopentane ring. And the common example is a ketonic derivative, which is phenchone, and an unsaturated derivative, that is alpha phenchene, which are largely found in the volatile oils of fennel, which is Phoenicallum vulgare, belonging to family Apiaceae, and commonly it is known as sonf. So friends, this was about the monoterpenoids, and in the next lecture I will start with the other classes, specifically with the sesquiterpenoids, and we will discuss about the other classes like sesterpenoids, diterpenoids, tri, tetra and polyterpenoids, along with their therapeutical uses. Thank you.